right? A few pieces of information that we need, right? The specific heat of water, right, is 4.184 right, joules per gram degrees Celsius. And you got two things that are happening, right? I've got 55.9 grams of water, and that water goes from 99.21 degrees Celsius and it drops down to 96.9 degrees Celsius. As that's happening, I've got zinc. I've got 23.9 grams of zinc, and it starts off at 21.1 degrees Celsius. What's the final temperature of the zinc? 96.9, right? That's the water stops at 96.9 because you've reached thermal equilibrium, right? So the zinc goes all the way from 21.1 to 96.9 degrees Celsius. So now we're going to do the same calculation twice. We're going to do Q equals MC delta T. We're going to do it once for the water, right? So Q for the water equals MC delta T. So Q for the water, right? My mass of water, 55.9 grams. My specific heat of water, 4.184 joules, grams, degrees Celsius. And my delta T for the water, right, negative 2.31 degrees Celsius. So we multiply those all together, right? Q for the water minus 540.28 joules. So that tells us the water lost 540.28 joules of energy, right? Now we want to do the same calculation for the zinc, right? Q equals MC delta T, where we know the mass, right? I know the mass is 23.9 grams. I know I can find delta T because I know initial and a final temperature. We're looking for our specific heat of zinc. What is the energy? What's Q for zinc in this problem? Yeah, 540, a positive 540.28 joules, because the water lost this energy, right? Water lost this energy because zinc gained this energy to go from 21 to 96.9 degrees Celsius. So Q for the zinc, we just flip the sign, right? 540.28 joules equals my mass, 23.9 grams, right? My specific heat is what we're looking for. And my delta T is like 75.8 degrees Celsius, right? Multiply, we divide that across. I get a specific heat for the zinc of approximately 0.298 joules per gram times degrees Celsius. I would go with 3 significant figures because I've got 3 significant figures in the mass, right? 3 significant figures in that mass. And even in our temperature, right? We've got 3 significant figures in our temperature change as well. So I would answer that to 3 significant figures. So something like 0.298 joules per gram times degrees Celsius. Yeah. Yeah, Q equals, so the question was like, what was the other equation that we had? Q equals C delta T. That C is our heat capacity. So that would be like the entire calorimeter, right? There's no mass component because the units of our heat capacity are just joules per degree Celsius. So it's for the entire thing. It doesn't matter the mass because it's not per gram, right? It's for the entire calorimeter. So that's Q equals C delta T. Here we need Q equals MC delta T because, right, we've got a mass of water that's going through a temperature change. You got a mass of zinc that's going through a temperature change. The important thing was to realize that because they're in the same system, right, that the energy that at the calorimeter, the energy that the water lost had to equal the energy that the zinc gained to go through that temperature change. And with that, we could find our specific heat. Yeah. If the question had asked for the Q of the zinc, right, trying to think how we would do that. I guess given the information that we have, right, we're looking for the specific heat. Like a case where we would be looking for the Q of the zinc would be, you know, we have this temperature change, we have this specific heat to this mass of zinc. You know, how much energy did that zinc absorb? So in this case, it's hard to kind of think of this as just like, let's solve for the Q of the zinc. It would be a little bit different question, and we'd have a little bit different information given to us. Yeah. All right, any other questions on 42? Yeah. Right, this is in the calorimeter, yeah. So, right, this is in a closed system. So any heat, right, there's no heat transfer to the outside. So any heat that the water loses, right, anything else in that system has to absorb that heat because there's no transfer outside of the calorimeter. So if the zinc absorbs this much energy, right, we could even work backwards. The water had to lose that much energy because, again, there's no transfer outside the calorimeter. Yeah. Do you have a question as well?